for this example, we want to solve the given nonlinear system of equations. And we say that this system is nonlinear because there are terms that involve x and y that have degrees, in this case 2, that are bigger than 1. But we can apply similar techniques that we used with linear systems to solve nonlinear systems. So for example here, we can use the elimination method that you recall from linear systems of equations. And what that means is I can combine equations 1 and 2 so that I can eliminate, for example, the x squared term in equation 2. And by multiplying the top equation by minus 4, that would give me minus 4x squared minus 4y squared is equal to minus 16. And adding that with equation 2 below it, we see that the x terms, in this case the x squared terms, would cancel out. So we get a cancellation here and here, and combining the y squared terms, we get 5y squared remaining. And combining the constants on the right side gives us 20. And now we have an equation of just one variable, y, that we can solve for y. And dividing both sides by 5 gives me y squared is 4. Taking the square root of both sides gives me that y is plus or minus 2. So there's two solutions for y. So that means any system, any solution that solves this system, when I must have y is equal to 2 or y is equal to minus 2. And so let's find out what the corresponding x values would be to go along with those y values. So we have two cases here. First case is if y is equal to 2. I can plug this into either of the equations. Let's say we plug it into the top equation. Then I would get x squared plus y squared, which is 2 squared, which is equal to 4. So that says that x squared, therefore, is equal to 0, and x must be 0. So if y is equal to 2, then x must equal 0. So this means we have one solution at the point 0, 2. And similarly, taking the other possible value of y, if y is equal to minus 2, we get a very similar solution when we plug this back into the top equation. Once again, when I square the minus 2, that gives me 4 on the left side, and then subtracting that 4 from both sides would give me x squared is 0. So again, if y is minus 2, then x is going to equal 0. So we have a second solution here at 0, minus 2. And we can check our answer, it's never a bad idea, by taking these values and substituting them into each of the equations above and making sure when I plug in these values into the left side, they give me the corresponding values on the right side. And so notice here, we have two solutions. With linear systems of equations, we saw it was possible to have 1 or 0 or infinitely many solutions. And we can get similar sort of solutions with nonlinear systems. We could have 1, 2, more than 2, or possibly none. To see another method that we could have used to solve this one, and never hurts to see multiple ways of solving these problems, since in some cases one might be nicer than the other, we could have used what's called the substitution method. And this method is what we do when we can say solve for x squared in the top equation by subtracting y squared from both sides. Now I can plug this into 4x squared in the second equation. So I would get 4 times 4 minus y squared plus 9y squared is equal to 36. And so distributing the 4 gives us 16 minus 4y squared plus 9y squared is 36. And combining the y squared terms, I get 5y squared. Subtracting 16 from both sides, I get 20. And so this gives me y squared is equal to 4. And so y is equal to plus or minus 2. And so notice at this point, we get a consistent equation as we did from the first example. And then we would solve this the same way, namely by taking these solutions and plugging them back into either of the equations 1 or 2 to solve for x. And we would get the same solutions over here. So this system of nonlinear equations has two solutions. And we can also take a look at this visually. So I'm going to move over to the next slide to look at the graph of these two equations. And so what we're looking at here in the graph in red is the top equation. Okay, this, recall, we saw is a circle. And the second equation, since the coefficients in front of the x squared and the y squared terms are not the same, this is actually an ellipse, which is sketched in blue below. And the solutions are going to be intersection points. And in this case, both of these graphs are not graphs of functions. These are not functions, but we can still graph each of these equations, and we can look for intersection points. And we see there's one intersection point at 0, 2. There's a second intersection point at 0, minus 2, and this is consistent with the algebraic solutions we found on the previous slide.